All right, our second related rates example. We've got Maria flying her kite. It's 100 feet above the ground, and the wind causes the kite to move horizontally at a constant rate of 8 feet per second. In order to maintain the kite at a height of 100 feet, Maria must allow more string to be let out. So Maria's not moving. She's standing in one spot and letting the string out. At what rate is the angle between the kite and the string changing in radians per second when the string is 200 feet long? Okay, so we're going to have to draw this one. Here's the ground. I think I can handle a kite. Not bad. So the kite is 100 feet above the ground. Is that ever going to change in this problem? No, because what she's doing is maintaining it at that height. So I'm going to label that side with 100 because it doesn't change for the whole problem. You should never put a number on a diagram in a related rates problem if it changes, if it's a quantity that's changing. The in the moment numbers do not belong in your diagram. Okay? They belong in your want section. What do I want? And here's that moment information. Really important. So I got to put Maria somewhere. Again, I'm amazing at drawing. So this is Maria. Hi, Maria. And she's got string. So I'm going to label that with an S, right? Up to the kite. So what's happening? The wind is causing the kite to move horizontally at a constant rate of 8 feet per second. And she's having to let out more string. So if the kite was moving this way, she'd be letting in string. So the kite must be moving that way. Kite is going this way. Okay. Which means as the kite moves, right, the kite's going, oopsies, that wasn't what I was trying to do. The kite's going this way, then this S is going to flatten out a little bit. This angle is going to get smaller. And the S will get longer. The 100 will stay, but this side will also get longer. So I'm going to label that side with a variable 2 because it is also changing. Okay, so back to trying to make sense of this. The wind is causing the kite to move horizontally. Aha. Now I see that I have a rate. So I figured out which direction it's going. And if it's moving at 8 feet per second, how is that changing something in this triangle? What is my known rate? Did you say dx dt? Well, that looks like a y. I hope you did, because that is exactly the part of the triangle that corresponds to moving this way at 8 feet per second. And it's getting bigger or smaller? Bigger. So we know that dx dt equals 8. Now, what are we looking for? At what rate is the angle? Oh, I need to label an angle in here between the kite and the string. The kite and the string. Ah, so that's got to be this angle right here then. The kite and the string, not Maria and the string or the string and the ground, but the kite and the string. So I'll label that with a theta. And that's what I'm looking for is a d theta dt. At what moment? When the string is 200 feet long. Okay, once again, if it takes you a minute, press pause so that you can kind of reread, redigest our diagram, and make sure you understand where the knows and the wants are coming from. What we need to do next is come up with an equation that relates what I know, which is the x, what I know about, and what I want, which is the theta. Okay. Notice that I do not have any information about the rate of change of s. So when I write an equation, I do not want s involved because I will not be able to fill in what ds dt is. So theta and x, what else do we know? Theta, x, what is this? Sure looks like a tangent to me. Opposite over adjacent. So this is one where, again, we're using a geometric formula, but we have to make sure we pay attention to the things we want to know about and the things we do know about, and we leave out the things we don't. So go ahead and press pause on this one. If you get to this point, I want you to take the derivative of both sides with respect to t, fill in your knowns, see what you get. All right, so I took my derivatives, secant squared theta times d theta dt, and 1 over 100 times dx dt. Divide both sides by secant squared to get the d theta dt by itself. But if you divide, if you have a secant squared on the bottom, don't you have a cosine squared on the top? And then I just filled in what the cosine would be. In that case, it would have been adjacent over hypotenuse. We knew that the S was 200 in the moment, and filled in these values to get 1/50 radians per second.